Welcome to this Maths Made Easy video on the Arithmetic series. And to start with, we want to be aware of what we obtain when adding the terms. And what we mean here specifically is the sum of the first n terms. If we have a formula for the sum of the first n terms, then we can apply this for any arithmetic series. So in that case, first we'll give the result, and then we'll show the derivation of that result. So the formula here for the sum of the first n terms is simply given as s subscript n here, which is equal to n times a plus l divided by 2. And remember here, for an arithmetic series, a represents the first term in our series and l represents the last term. N is simply the number of terms that we want to sum for. So for example, if we wanted the sum of the first 10 terms here, this would be s subscript 10, and this n here would be a 10, for example. Now, how do we prove this result? Well, first let's just take a general series here. So we've got the sum here of the first n terms of a general series. Well, we know the first term is simply a. So if I want the next term in this series, it's going to be a plus the difference, a plus d. That gives us the next term in our series. And then clearly, this series would resume here with the next term being given by a plus 2d. Okay, and this will carry on all the way up to the very last term. So this is all the way up to the very last term. But before this last term, we have the last term minus the difference here. Okay, that would be the penultimate term here in our series. So in that case, the final term is simply given by L, the last term. And if we consider this series almost going backwards now, so Sn again, but this time starting with the last term here, well, we've got the last term. And again, working backwards here, my next term is going to be plus L minus D. Okay, and in that case, the next one would be plus L minus 2D. And this would resume all the way until we get to our very first term here. Okay, so again, this carries on all the way up to our penultimate term, a plus d, and then finally plus a. Well, now let's consider what would happen if we were to add these two terms, or these two series together. Well, if we add these two series together, we'd get Sn plus Sn, so that would give us two lots of Sn. And between each term here, each series, we'd have a plus l, so that would be my first term there. That would be a plus l. In this part here, we'd have a plus l, and then we've got this d here plus minus d, so those d's will cancel there, which simply leaves me with a plus l. So we obtain another a plus l. And again, this would keep repeating here. This minus 2d will cancel with this 2d, and again, we just get a plus l there. Okay, and this carries on for an nth number of times here. So this would just keep carrying on to our final a plus l. Now, like we just said there, this occurs n number of times. Okay, so in that case, we can define two lots of Sn simply as n lots of a plus l. And in that case, if we simply want Sn, and we can see we're extremely close to this result here, we would just divide here by this 2. So therefore, Sn is simply given by n lots of a plus l divided by 2 there, giving us the result that we started with. And it's worth mentioning, just to finish with here, that we can substitute L equals, so substitute L equals here a plus n minus 1d into this expression here for the sum of the first n terms, and we can obtain the longer form here for the summation of the first n terms. Okay, so if we substitute this into Sn, what we also obtain for Sn is n over 2 times by 2a plus n minus 1d there. Okay, so that's the other expression that we can use for the sum of the first n terms there. Moving on now to take a look at sum notation. So when we're taking a look at sum notation here, we use a Greek letter to represent this. And the Greek letter that we use here is capital sigma. Okay, so this is sigma here, and this represents the sum. Now we can use this instead of Sn for an arithmetic series. So for example, if we was to write the sum here of 3n plus 4 from n equals 1 to 20, this would be the sum of the first 20 terms, or the sum up to the 20th term, of the arithmetic progression defined by 3n plus 4. So all this means here is we start with n equals 1 and we keep going to the 20th term there. Okay, so that's how we read that notation. Finally, moving on now to arithmetic progressions for natural numbers. So here, let's consider the sum of the first n positive natural numbers. Well, in that case, we could simply write the sum here, Sn, as being equal to 1 plus 2 plus 3, and this would carry on all the way up here to our last term, our last positive natural number here, which we'll denote as n. But before that, we would have n minus 1 here. Okay, so our penultimate term would be n minus 1, and our final term would be n. Well, in that case then, we can simply identify the first term in our progression, we can identify the last term, and the total number of terms here. So simply, the first term here, a, that would be 1. So our first term is equal to 1. The last term here is simply given by n. And the number of terms, n, is simply equal to n. That's just defined by how many natural numbers we're using here. So n equals n. So, using the sum of an arithmetic progression here, so using Sm is equal to n times a plus l divided by 2 here, with the appropriate a, l and n in this case then, and what we can obtain here is the sum of the first n positive natural numbers here being defined as Sm is equal to n times a, which is 1, plus l, which is n. This is all divided by 2. And in that case, we can write it in a more familiar form here, which is a half n times by n plus 1 there. Okay, and that gives us the formula that we need there for the sum of the first positive, or the first n positive natural numbers there. And that concludes this Maths Made Easy video on the arithmetic series.